Today I'm here to talk about high-speed machining. One of the hardest things about high-speed machining, or HSM as it's abbreviated, is that people define it in so many different ways. For some, it's all about high spindle speeds and the feed rates that go with them. For others, it's about smaller step-overs and even more accelerated feed rates as chip thinning starts to take effect. And for still others, it's all about the special cam toolpaths that ensure constant tool engagement angles. HSM really does mean a lot of things to different folks, but it's best to think of it as a coordinated set of techniques designed to increase your machining productivity. Most people agree that HSM does greatly increase machining productivity, but how does it do that? There are two challenges to faster machining. First, heat limits the spindle speed you can run the cutter at. Once the cutter gets hot enough, it softens, the cutting edge dulls more easily, and the tool is soon finished. The other issue is chip load, and especially chip clearing. If the chips can't be moved out of the way fast enough, they'll clog the flutes of the cutter, it'll jam, and probably break not long after that. High-speed machining attacks both problems. Here's a big surprise for most machinists to discover, and we can see it here on this chart. At a certain point, increasing your surface speed and therefore your spindle RPMs will actually reduce the heat. Wow, I didn't see that coming, did you? But this was first noticed way back in the 1920s. In fact, Carl Salomon proposed taking advantage of it for machining in 1931. And the chart you're looking at is called Salomon's curve. Check it out. We see the heat going up sharply here all the way on the left as the surface speed and spindle RPM increase. But all of a sudden, it drops off. That point where the heat drops off is where high-speed machining begins. Have a look at aluminum and non-ferrous metals here. The heat starts falling off at around 400 meters per minute surface speed. That's about 1,200 surface feet per minute in imperial units. The turnaround point is higher for ferrous materials and particularly tough alloys, but with high quality cutters and the right coatings, we can get there and machining productivity goes way up when we do. We saw how HSM takes care of the heat problem, but now let's turn to clearing the chips. The answer here is to run smaller step-overs. If less of the circumference of the tool is involved in the cut, more of it will be exposed to air and coolant. Chips are much easier to fling away from the cutter because they don't have to be excavated up and out by the flutes. So, packing the flutes and breaking the cutter is much less likely. Exposing the majority of the circumference of the cutter to air and coolant also cools the cutter better, allowing it to tolerate even more heat. In addition, by climb milling, we're cutting chips from thick to thin. See how the chip is wedge-shaped? Okay? When we cut thinner and thinner parts, starting with the thickest, most of the heat is going to be trapped in that chip and carried away from the cut when the chip is flung out. All this adds up tremendously, and on top of that, we get faster feed rates still because of the effect of chip thinning. HSM lets us feed the cutter dramatically faster through the material, but we're not done speeding things up yet. Let's talk about high-speed machining toolpaths. That's what this slide is about. They provide what's called a constant tool engagement angle. The red cylinders in the diagram are end mills. I've only shown partial cylinders to show how much of the circumference of the end mill is involved in the cut. That purple is the material we're trying to remove from the blue part. And the cutter is traveling right to left into a corner. And notice what happens when the cutter enters the corner. The tool engagement angle just about doubles. It goes from the 90 degree, the 1/4 cylinder, to 180 degrees, a half cylinder. And it does that very suddenly. It's like it's a traffic collision, right? So suddenly cutting forces are doubled. Chip clearing gets twice as hard. Slamming into corners is really hard on cutters, but before we had HSM toolpaths, we used to just do it all the time. Every toolpath did that. In fact, even today, manufacturers' recommended chip loads are based on the worst case assumption that we have to deal with these kind of corners. If we could avoid those corners, we could run much faster than even the manufacturer's recommended chip loads. And that's exactly what HSM toolpaths are designed to do. Let's take a look. Okay, here are toolpaths for the same pocket side by side. The one on the left is an HSM toolpath. That cutter never sees a corner. It just follows all those little curly cues and it never jams into a corner. Tool engagement angle is constant. The other is a conventional toolpath and it's full of corners. Here's another example. This is called trochoidal slotting. And the tool goes in, following the curly cues. Slots are some of your worst challenges in terms of very high tool engagement angles, but an HSM toolpath like this fixes the problem very nicely. If you've never used an HSM toolpath, by now you're wondering how much faster they can be, and the answer is lots faster. Here's some data I put together comparing various pocket roughing strategies using my G-Wizard speeds and feeds calculator. G-Wizard does HSM feeds and speeds very nicely, and as you can see, running various different roughing strategies, whatever we pick, adding HSM on top of that always helps. If we use the same end mill for roughing and finishing, it gives us a 56% advantage over a non-HSM toolpath. That's a lot. You can do even better with some of these other strategies. Rust machining lets you use a bigger cutter and then come back and finish with a smaller cutter that fits into the corners. The point is, every single roughing strategy we try benefits from HSM, no matter what we started from. Your advantage with HSM is going to vary by material, but there's an advantage for every material I simulated here. And you can see it varies from what you're getting from aluminum up to really tough materials like titanium. If you're not using HSM for roughing in your shop, you're missing an important